Let's do a simple center of mass problem. I have four masses located on the x-axis at various locations shown here, and we're going to find the center of mass of this system. Here's our formula for determining the center of mass of point masses. When you have a solid object, these summations turn into integrals. But right now I'm going to focus on point masses. We're going to add up all of the masses multiplied by their locations, and we're going to divide by the total mass. So in this particular case, I've got m1 multiplied by x1, m2 by x2, all the way up to the fourth mass times its location, and I'm going to divide by the total mass. Basically, it's a weighted average. So we're going to find the x center of mass if m1 is 1 kilogram, m2 is 2 kilograms, m3 is 3 kilograms, and m4 is 4 kilograms. 1 kilogram multiplied by its location, and m1 is located at -2 on the x-axis. m2 multiplied by its location, and it's at 0 on the x-axis. m3 is 3 kilograms, and it's located at 3 meters on the x-axis. I'll assume x is in meters. And m4 multiplied by 8 meters, and we're dividing by the total mass. The center of mass of the system is located at 3.9. And that's the location where all the mass appears to act from for this system. It's a weighted average that tells us what equivalent location can we put one mass that acts similar to all of these masses. So if we were to balance this system, if these four masses were connected this way on a massless rod, and we wanted to know where were we going to balance it, we would balance it at 3.9 meters. That's the location where it would balance. So this is a very simple one-dimensional problem. There's a problem worked out on the video solutions with a similar setup, but with 2 dimensions. So you're finding both the x and y locations of the center of mass. There's also a video solution worked out with a solid object where you have to do some integration. So those are how you would find the center of mass of various setups. But right now let's talk about why we're doing center of mass. Why does it show up in the momentum chapter? When you have situations where you can use momentum conservation, we know there's no external forces acting on the system. And if there's no external forces acting on the system, only internal forces are involved. And if only internal forces are involved, the motion of the system cannot change. I always tell my students, you can't make your car go faster by pushing on the dashboard when you're sitting in the car. Internal forces can't change the motion of the system. You have to reach out and put your feet on the ground and push on the car if you want it to go. You have to get external forces involved. So if you have a system that has a certain motion to it, like for example 2 ice skaters standing close together with their hands touching, and they're not moving, and then they push off each other so that one of them moves in one direction and the other one moves in the other direction. Initially, nothing was moving in this system. The system was stationary. The center of mass of the system is located right here, and it was not moving. And if no external force acts on the system, the center of mass can never move. It has to always be located at that spot. So as these two objects move apart from each other, what do we know? We know the center of mass always has to have a speed of 0. It has to remain in the same place. It's another way of looking at momentum conservation. It's exactly the same idea. And a lot of times, books teach solving these problems by going into what they call the center of mass frame, where you pretend you're sitting on the center of mass and you're watching all the motion, and the momentum about that point always has to be 0. So it's an interesting way of solving momentum problems. Let's take a look at another example where center of mass is a good approach for solving the problem. Let's say we have a cart and we have a person standing at one end of the cart. The center of mass of the cart is going to be in the center of the cart. If the cart is uniform density, then the center of mass is going to be located right there. And the center of mass of our person is going to be located at the center of the person. And the center of mass of our system is going to be somewhere about here. If we have an isolated system, a cart with frictionless wheels and a person standing on it, and the person walks to the left across the cart, as the person walks to the left, the cart's going to move to the right. So at some time later, it's going to look like this. So the person starts to walk to the left, and now we have this situation. The person's moved a little bit to the left, the cart's moved a little bit to the right, the center of mass of the cart is now here, the center of mass of the person is at the person's location, and the center of mass of the system has not moved at all. It's in the exact same place it was last time. Because it was not moving initially, I guess I should write that here. It cannot move at any other time without some external force acting on the system. So as the person walks to the left, here's time 1. The center of mass is not moving. The person's all the way at the right. The person starts to move to the left. The cart moves to the right. The center of mass of the system cannot move because these are only internal forces. So at time t2, the center of mass of the system is still in the exact same place. It's not moving, even though the person's moved to the left and the cart's moved to the right. The person continues to move. The center of mass of the system remains at the same place. The person continues to move. The cart continues to move. The center of mass of the system remains at the same place. And finally, the person stops at the other end, and the cart stops, and the center of mass is in the same place. Finding the center of mass at the beginning and at the end is an interesting way to solve this problem and see how far the cart has moved. So let's do that. Let's have the mass of the person be 75 kilograms and the mass of the cart be 100 kilograms and the length of the cart 4 meters. The first thing we want to do is pick our coordinate system. Why don't we take the left end of the cart? So this will be x equals 0. And we know the center of mass of the cart is in the center of the cart. So let's find the initial x center of mass. We need the cart and the person. Those are our two objects in the system. And what we're going to do is treat this as if those objects are point masses. We're going to replace the person with a point mass of 75 kilograms at that location. We're going to replace the cart with a point mass of 100 kilograms at the location of its center of mass. And then we're going to find the center of mass of those 2 point masses. So this is 100 kilograms times 2 meters. That's this distance right here. It's 2 meters. Plus the person's mass times 4 meters. That's where they're located. So the center of mass of the system is 2.86 meters to the right of the edge of the boat. So this is 2 meters, so that's this distance. Now we're going to measure the center of mass after the person's moved all the way to the end, this last drawing. So the boat's center of mass is still at 2 meters, as measured from the end of the boat. And the person is now at 0 meters. They're at the edge of the boat. They're at our origin. .14 meters. And what you'll notice from looking at these two pictures, so what you notice from looking at these images is that the left edge of the cart started out 2.86 meters to the left of the red dashed line. And the red dashed line, that represents a fixed place on the ground. The center of mass of our system never moved with relation to the ground. The cart started out 2.86 meters to the left, and as the person walked across the cart, it ended up at the end only 1.14 meters to the left of the red X. So how much did the cart move? That distance is 2.86 minus 1.14. So the point here with center of mass problems, anytime you have a situation like this, a frictionless cart with somebody moving across it, a boat, somebody walking across a boat, and a frictionless setting where the boat is moving freely in the water without friction between the boat and the water. These types of problems are easy to solve using a center of mass approach. These are simple one-dimensional problems. Don't forget, the video solutions deal with a two-dimensional problem with point masses and a solid object where you have to integrate over the object to find the center of mass.